the end of elliptical orbits. In this video, we find out the minimum radius possible for elliptical orbits and circular orbits, according to general relativity. Formerly, we calculated Mercury's perihelion precession and claimed our calculation is valid so long as the perihelion radius is greater than 6 gm. But do any smaller orbits exist at all? Let's start with Mercury's orbit as an example. Mercury's perihelion is 46 million kilometers, or about 33 sun diameters away. Let's get a sense of what that looks like. Okay, the Sun and the distance to Mercury are scaled properly now. Only Mercury's size has been exaggerated by a factor of about 200 or so that you can see it on the screen. But how far away exactly is 6 gm? Putting in the value of g, Newton's universal gravitational constant of 6.67 times 10 to the negative 11 meters cubed per kilogram second squared, and the mass of the Sun, 2 times 10 to the 30 kilograms, we cancel the kilograms, but are still left with the units meters cubed per second squared. Remembering that we always leave out the speed of light in our expressions, the meters cubed per second squared signals us that we must divide by the speed of light squared to obtain units of distance. We find that 6 gm corresponds to a distance of roughly 9 kilometers from the center of the Sun. The Sun itself has a radius of 700,000 kilometers, so this kind of orbit around the Sun is impossible. However, if we replace the Sun with a black hole, this kind of orbit is possible, since all the mass is concentrated into a geometric point. To explore elliptical orbits less than 6 gm, our starting point is the orbit equation that we developed in the video entitled Mercury's Perihelion Precession. This equation has some interesting terms. The first term on the right is a radial kinetic energy term. The second term is just the Newtonian potential energy. The third term is an angular kinetic energy term. And the fourth term is unique to general relativity and clearly exerts its influence strongly and overwhelmingly at small radii only. The term on the left-hand side is a constant of the motion. Since it is equal to the sum of the energy terms on the right, we can think of it as the total effective energy. Let's call the last three terms VR, and take the derivative of the equation with respect to tau. The dr by dtaus cancel, and we see that the acceleration of the orbiting planet in the radial direction is equal to the negative of the slope of v of r. Let's graph this function v of r and see what it looks like. We have graphed the function v of r for an L value of 5 gm. Let's also put the total effective energy on the graph. I have used a constant value of about 0.05 for the total effective energy. Now the radial kinetic energy, when added to v of r, makes up the total effective energy, and so the radial kinetic energy is the difference between the two, as pictured on the graph. For this energy value, we see that the orbiting planet, let's call it planet X, falls inward faster and faster until a certain maximum. After this point, the radial velocity of planet X reduces to 0, which is the perihelion point, or the planet's closest approach to the black hole. We see at this point that the radial acceleration is positive because the slope of v of r is negative, so planet X is pushed out again and travels off to infinity. This is an unbound hyperbolic orbit. If we want an elliptical orbit, we need to lower planet X's total effective energy. Now that the effective energy is negative, we see that there is another position where the radial kinetic energy is 0, and this is the outermost orbital position called the aphelion. Notice that the slope of VR is now positive, so the radial acceleration is negative at the aphelion. Therefore, planet X reaccelerates inward. This is a stable elliptical orbit with both a perihelion and an aphelion. But what about the point in the middle where the slope is 0? Is there anything special about that point? The answer is yes. If the total effective energy is lowered to this point, it is where a stable circular orbit occurs, because there is no radial motion, since the radial kinetic energy is 0, and there is no radial acceleration, because the slope of V of r is 0. We can find out this location by taking the derivative of V of r and setting it to 0. To solve this equation, we first multiply through by r to the power of 4. We solve this quadratic equation in r using the quadratic formula. We will simultaneously solve for L squared, to be used later. Now let's factor out an L squared in the equation for r. If we use the plus sign and our value of angular momentum, which is 5 gm in this example, we arrive at an r value of about 21.5 gm. However, there seems to be a second answer for a circular orbit. If we use the minus sign instead, we get an r value of about 3.5 gm. What does this second answer mean? Well, the second position, where there is no radial acceleration, is way up here at the top. In order for this to happen, we need to bring the total effective energy up to this position. In this situation, a planet coming in from infinity will find itself captured in a circular orbit at r equals 3.5 gm. However, this circular orbit, unlike the one at 21.5 gm, is unstable because a small push inwards will find negative radial acceleration towards the center of the black hole, whereas a small push outwards will find positive radial acceleration out towards infinity again. Let's bring back the two circular orbit equations we developed earlier. We immediately see that r less than 3 gm is forbidden, since L squared is a positive quantity, and r equals 3 gm corresponds to an angular momentum per unit rest mass of infinity. This is achieved by light itself, which has 0 rest mass, and may therefore circulate in orbit around a black hole at r equals 3 gm. Massive objects can approach this radius if their angular velocity approaches the speed of light. R equals 3 gm is therefore the smallest possible unstable circular orbit. To find the minimum radius of a stable circular orbit, this corresponds to the plus sign in our expression for the radius of a circular orbit, since the stable circular orbits occur further out than the unstable ones. We see that the smallest circular orbit possible when using the plus sign occurs when the square root term is 0. Solving for L squared and plugging it back into the equation for r yields a minimum stable circular orbit of 6 gm. This happens for an L value of root 12 gm. So let's see what V of r looks like at that L value. The curve at this critical L value does not appear to have a stable valley shape. A stable valley shape implies a positive second derivative of V with respect to r, because that would mean the slope is increasing. Let's find out if this second derivative is in fact positive. We bring down our expression for dv by dr and take one more derivative. Let's remember the relationship between L and r for a circular orbit and plug it into the equation. Now let's put everything over a common denominator. Expand out the brackets. Now let's collect like terms. And now let's factor out a gm from the numerator. If r is greater than 6 gm, we get positive over positive, which is positive. This represents a stable circular orbit. If r is between 3 and 6 gm, we get negative over positive, which is negative. A negative second derivative when the slope is 0 indicates a curved top, because it means dv by dr is changing from positive to negative, and is therefore the location of an unstable circular orbit. The case of r equals 6 gm, as pictured in the graph, has a second derivative of 0, meaning that the graph is neither concave up nor concave down. Any slight nudge inward will result in planet X falling towards the center of the black hole, and any slight nudge outward will cause a brief increase in radius, followed again by a fall towards the center of the black hole. So this case behaves in an unstable way, although it is often called marginally stable or neutrally stable. Therefore, the smallest possible stable circular orbit occurs at r just slightly greater than 6 gm. It is interesting to note that any circular orbit between 3 and 6 gm inclusive is unstable, and any circular orbit greater than 6 gm is stable. Now let's turn our attention back to elliptical orbits. For any given angular momentum value, the smallest possible perihelion occurs up near v of r equals 0, where it crosses the axis. To find this point, we set v of r to 0 and solve for r. Now let's use the quadratic formula. Let's clean things up a little. We choose the plus sign in this result, since the minus sign does not correspond to a planet in an elliptical orbit. The minus sign corresponds to an additional orbital state, in which a planet goes back and forth through r equals 0, which I touched on in my black hole parts 1 to 3 videos. It is clear from this expression that the smallest value of r occurs when L is reduced so far that the term inside the square root vanishes. Setting this radicand to 0 leads to an L value of 4 gm. Substituting this back into our expression for r yields a minimum possible perihelion of also 4 gm. Let's see what that looks like on the graph. We see this point actually corresponds to an unstable circular orbit at 4 gm, but we need slightly less total effective energy anyway to have a finite aphelion, so the smallest possible elliptical orbit has a perihelion just slightly greater than 4 gm. This brings us to a curious place. We showed in the previous video that we can calculate the precession of elliptical orbits to arbitrary precision as long as the perihelion is greater than 6 gm. But now we have discovered that elliptical orbits can go down to 4 gm. Does that mean there is a small range of elliptical orbits where this method doesn't work? The 6 gm number was based upon a binomial expansion with an x value of 2 gm times 2up plus ua needing to be less than 1 for the expansion to converge. However, let's now be more careful in estimating the size of this x value. Remember that u was defined in the previous video as 1 over r, so let's make that substitution. And now let's solve for the kinetic energy term, 1/2 dr by d tau squared. And now let's factor out the cubic's leading coefficient, GML squared. The cubic equation in U can be factored into three roots, UP, UA, and US. These are the turning points of the planet for a given energy and angular momentum, since it is at these U values where dr by d tau is 0. UP will be our perihelion turning point, UA our aphelion turning point, and US will correspond to the turning point that is not part of the elliptical orbit, as discussed in the last video. It is important to note that US is greater than UP, which is greater than UA, since U equals 1 over R. Let's expand out these brackets so that we can compare coefficients. We will now equate the U squared terms. We solve for UP plus UA and substitute this into our expression for x. We arrive at a final result which tells us that x is always less than 1 for any elliptical orbit, because US, the third turning point that is not part of the ellipse, is always greater than UP, remembering that U is 1 over R. We only run into trouble if US equals UP, but in that case the orbit is not elliptical at all. Instead, the planet is captured in an unstable circular orbit at UP. So the method we used in the last video for calculating the precession of Mercury's perihelion works for any and all possible elliptical orbits. However, in cases where US and UP are close together, and they can be arbitrarily close together if the angular momentum is less than 4 gm, many terms in the binomial expansion will be necessary for reasonable accuracy. Thank you for watching.